Hey everyone, today we're going to be seeing what would happen if a white hole and a black hole collided. So I'm going to be showing you what a real white hole would look like compared to a real black hole, what it would look like when they combine together, and I'm also going to be showing you a real experiment you can do that would simulate this. Now, if you solve Einstein's field equations, you can predict that black holes should exist, but you also predict another thing that exists called a white hole. Now, white holes are similar to black holes. They're a different solution to the field equations, and they have some different properties. One of these properties is that instead of nothing being able to escape the event horizon like a black hole, for a white hole what it means is that nothing can enter the event horizon. So nothing can actually go into a white hole, whereas nothing can actually come out of a black hole. So a white hole and a black hole are actually very similar. A white hole is just a time-reversed black hole. In relativity, it's important to choose your coordinate system wisely because time and space depends on gravity and speed. Now, the easiest way to understand the difference between a white hole and a black hole is to talk about a coordinate system in which you're free falling. In this coordinate system, a black hole appears as though it is sucking in space-time. So space-time is ever flowing inward towards the center of the black hole. But for a white hole, space-time is always flowing outward, away from the center of the white hole. So remember that in a free-falling coordinate system, black holes are sucking in space-time and white holes are spewing out space-time. Now here's where it gets interesting. So for a black hole, it's always sucking in space-time. And the closer you get to the center of the black hole, the faster it's sucking in space-time. So for example, picture a drain with water flowing. As you're further away, the water's not flowing very fast, but as it gets closer and closer to the center of the drain, it speeds up faster and faster until it gets extremely fast right at the center of the drain. Now, at the very center of the black hole is a singularity, and at that point, space-time is getting sucked in at an infinite rate. But that's not the interesting part. The interesting part is actually a little bit away from the singularity, called the event horizon. At the event horizon, that is the point at which space-time is flowing inward at the speed of light. So that means exactly at the event horizon, light cannot escape because space-time itself is being sucked inward at the speed of light. And so photons can't go any faster than that, so they are forever held at the event horizon. Now, inside the event horizon of a black hole, space-time is actually flowing faster than the speed of light. And so that's why nothing can ever escape from the black hole, because inside the event horizon, space-time itself is moving faster than light, and nothing can move faster than light, so it can never escape it. Now, this still doesn't violate Einstein's law that says nothing can move faster than the speed of light, because that law is talking about objects in space-time in reference to each other. They can't move faster than the speed of light. But it's not talking about space-time directly. Space-time itself, while being sucked into the black hole, can move faster than the speed of light. So that's a black hole, but what about a white hole? Well, a white hole also has a singularity at the center. It's made of mass just like a black hole, so that means it also has gravity, so objects are also attracted to it and get pulled towards it. But here's where it gets interesting. When an object gets pulled towards a white hole, the object never goes into the white hole even though it's attracted to it. Well, remember I said that white holes, instead of sucking in space-time, they're spewing it out. It's flowing outward from the white hole. And so that means as an object gets closer and closer to the white hole, space-time is pushing out. So let's say you were moving at the speed of light going towards a white hole. Well, space-time itself is moving against you this time, so that means that you would just be completely stopped at the event horizon of the white hole. And since nothing can ever move faster than the speed of light, that means that nothing can actually get into the white hole. Because at the event horizon, space-time is moving at the speed of light and nothing can go faster than it, so nothing can get inside of it. Now, inside the event horizon, space-time is actually moving faster than the speed of light, going the opposite direction. So you can see that a black hole and a white hole are actually really similar. The only difference between them is the direction of flow of space-time. Now, previously I made a video about white holes, and in this video I showed you a real-life experiment that scientists have actually used to make predictions about white holes. It's actually a pretty simple experiment. All you need to do is turn on your kitchen sink. Now, you may have overlooked this pattern, This pattern shows up whenever you have a stream of water hitting a flat surface below it. And it's kind of this wall of water that forms. So you can define this inner circular area where I've taken a cross section of it here. You can call it the jump radius. So you can actually show that anything within this jump radius, anything within these walls of water or this hydraulic jump area, you can show that the water is actually moving faster than the speed of wave propagation. So what that means is that if you were to make a little splash in the water, make a wave here, the waves could propagate out. But if you made a little splash in the water here, the speed of this water is faster than the speed of wave propagation in the water. And so the wave itself could never get past this hydraulic jump here. So now here's where the comparison comes in. Anything that's inside of this jump radius is the equivalent to anything that's within a white hole. And the hydraulic jump here is similar to the event horizon of a white hole. So what that means is that once something or some information leaves this hydraulic jump here, it can never come back in. Now let's say this food coloring represents information or some object coming out of the white hole. You can see that something can come out of the white hole, so I start within the event horizon and I let it come out, and it comes out quite easily. See it come out? But you can see that once it's out, it can never come back in. It tries to come back in, but it can never get back in. If I try to get anything in it, try really hard, it can never get back inside of it. So what would a real white hole look like? Well, we now know what a real black hole looks like. So first let's see a real black hole, and then I'll show you what happens if that black hole were actually a white hole, how it would look different. So here's a rendering of the black hole at the center of our Milky Way galaxy. The first thing that you'll notice is that it's not very black at all. In fact, it's extremely bright. Now the reason it's so bright is because it's constantly spewing out radiation, Hawking radiation, and also because of the accretion disks around it. Now the accretion disks happen because as things approach the black hole, they approach the speed of light. And as they approach the speed of light, their time relative to ours slows down. And so basically it's as though they become frozen in time. Eventually they become redshifted out of view and we never actually see them enter the black hole. And so what you get around the black hole is basically this frozen ring of light. And you'll notice that everything is lensed because the black hole's gravity bends space-time, and so it's basically bending the light from the stars behind it, and so it appears as though it's this giant lens. So here's what it looks like approaching the black hole at the center of our galaxy. Now the part of the black hole that you can't see anything, that is the event horizon, in which no light can escape at all. So you'll notice that as you gaze into the black hole, you can't see anything inside of it because nothing can escape it. So now here's the interesting thing. Remember that I told you a black hole and a white hole are different solutions to the same problem. So what we can do in this simulation is actually just flip the black hole to a white hole. And so let me do that right now. Okay, I'm going to turn this giant black hole into a white hole. And done. So the first thing you'll notice is that the accretion disk disappears for the white hole. That's because space-time itself is pushing things outward, and so in a free-falling coordinate system, you can't ever stay around it, it's always being pushed outward. You'll notice that it still has the ion jets coming out of it. But now let's fly in towards the center of the white hole and see what happens. So you'll notice as we get closer, we still get the gravitational lensing effect, but you'll notice that there's no dark center. You can actually see inside of the white hole. That's because any light that is coming from the center of the singularity of the white hole is still exiting, so we can still see inside of it. So the inside of the white hole could be another universe altogether or a different part of our own universe. You can see this a little bit clearer when I put on this grid pattern and then look at the white hole. So you'll notice is that I go in towards the center of the white hole. Now you can see that there's almost like an entire universe inside the white hole. So now what would happen if a black hole and a white hole were now to combine together? First, let's do an experiment to see what would happen. So if a white hole can be simulated by pouring a fluid onto a flat plate and having it flow outward, then a black hole should be able to be simulated by having a fluid sucked into something. So basically, this is a really simple experiment to set up. If you turn on your water in your sink, that's the white hole, and the drain is the black hole. So first, let's see what happens when we combine these two together in a real experiment, and then let's do a simulation of it and see what happens and what it looks like. Okay, so you can see my white hole in the corner here. You can see that if I try to tap out a message, it can exit the white hole, but if I try to tap in a message, no message can get inside of it. And if I try to tap information inside of the black hole, nothing can get out of it. So now this is the easiest simulation you'll ever see. What happens when a black hole and a white hole combine? Well, you can see that the black hole just swallows up the white hole. Okay, now let's see what it would look like in real life. So just like in the sink experiment, the black hole basically swallowed up the white hole. Now, for a black hole that has more mass than the white hole, it's easy to believe that it would end up still being a black hole, meaning that space-time is being sucked into it. But what about if the white hole had a larger mass than the black hole? Would it end up being a white hole? Or what if a black hole and a white hole had the same mass and they collided together? What would it end up being? Well, at the heart of that question is the relationship between black holes and white holes. Black holes and white holes might seem very different, but they're actually just two sides of the same coin. In fact, if you're going just based off of gravitational effects, there's absolutely no way you can tell the difference between a black hole and a white hole. They both act exactly the same way. Now, there's a lot of theories surrounding black holes and white holes. Some of those theories are that black holes can turn into white holes and white holes actually can turn into black holes. And at the creation of a singularity, a black hole and a white hole are actually in a quantum superposition of both of them. So it's a black-white hole until eventually one of them emerges. And the reason you have to take into consideration quantum effects is because at the center of a black hole and a white hole is a singularity, so something extremely small, smaller than an atom. All of that mass is contained at that single point, and so quantum effects dominate. And so if you had a black hole and a white hole of exactly the same mass that came together, I don't know whether it would be a black hole or a white hole at the end of it. Now, with everything I've just shown you, keep in mind that white holes are purely theoretical right now. There's a few problems with the existence of white holes. First is that they don't obey the second law of thermodynamics. Now, Einstein's theory of general relativity doesn't take into account thermodynamics, and so we can have solutions to these equations that don't necessarily have to obey the laws of thermodynamics, and white holes are one of those solutions. Another reason why white holes probably don't exist is because they're very unstable. So you can show that white holes will extremely fast turn right into a black hole, even if there's some way that they can be formed in the universe. But the mathematics of Einstein's field equations led us to understand black holes before we even proved they existed. This could be the case for white holes, but we won't know until further research is done. So thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, remember to hit the subscribe button and hit the bell so that you can be notified when my latest video's out. and check out theactionlab.com to see the Action Lab subscription box, and click the link in my description to get the Action Lab experiment book. I chose 30 of my favorite experiments from my channel and I show you how to do them and set it up. And thanks for watching, and I'll see you next time.